afternoon. We have been studying cosmic distances, and I told you in the last class that at small redshifts these distances give us the Hubble parameter, and at large redshifts we can use these distances to determine the cosmological model that we are in. Further, I explained to you why it is necessary to go to a reasonably large distance. At very small distances, you are going to have large uncertainties due to the peculiar velocity. So, it is necessary to go to reasonably large redshifts and distances more than 0.01, redshifts of more than 0.01. Now, to determine distances, you need standard candles, and at large scales you cannot make out, I had told you that you cannot make out individual objects inside the galaxies. So, you have to use the entire galaxies as properties of the entire galaxies as standard candles. And our discussion in the last class was based on this. We had discussed how different galaxy properties are correlated, and one can use these to measure distances, to determine certain properties of the galaxies which can use the standard candles and then measure distances. So, this was the discussion of the last lecture. Now, there is an exception to what I had told you about galaxies. So, there is an exception to the fact that you cannot make out individual objects inside galaxies, distant galaxies. Okay, and this exception are the supernova. So, supernova are the exception, and supernova can be identified in very distant galaxies also. They are extremely bright. A galaxy, I have already told you, has of the order of 10 to the power 11 stars, 100 billion stars, and each star has a luminosity of the order of 4 into 10 to the power 26 watts. So, the luminosity of a galaxy is 4 into 10 to the power 37 watts. That is the typical luminosity of a galaxy. Now, the luminosity of a supernova when it goes off is comparable and possibly more than this, So, it is brighter than the entire galaxy, and you can easily make out the presence of a supernova in a galaxy. This is a transient event, it occurs. Okay, it is a transient event that occurs in the in a star's life. So, this is an example. This is a picture of supernova 1994D, and it occurred in the galaxy NGC 4526. Okay, so this shows you a picture of the galaxy NGC 4526. Now, in this galaxy you cannot make out individual objects, that's you can see here, right. You can see, what you can see is this the distribution, brightness distribution, which we had discussed in the last class, the surface brightness or the specific intensity distribution. You cannot make out the individual stars, but there is a supernova over here which you can easily make out. So, this bright thing over here is the supernova 1994D. It is very easily distinguishable. So, you can easily make out this very bright object in this galaxy. Okay, so, you can identify supernova as distinct objects in very distant galaxies also. This is not the supernova 1994D, this is just another supernova, sorry, this 1994D should not be here. So, this shows you two pictures of the same part of the sky. It is obvious that it is the same part of the sky. These objects, all of the rest of the objects are there. Now, look at this circle. This circle here at this date, 3rd October 1999, does not contain any source. Now, at a later date, 4th November, you can see that there is this source over here. So, this is a new source that has appeared, that is the supernova. Okay. Supernova, incidentally, just to give, nova is a new object in the sky, that is how the name came, nova. These novas are actually were observed much earlier, and these were stars which suddenly become bright and they appear as a new star. So, a faint star which you cannot see suddenly becomes brighter, so it appears as a new star, nova. A supernova is a much bigger version of this. It occurs at the end stage of massive stars when they finish all their fuel. Okay. And at that point they become extremely bright. So, this is a supernova that has appeared over here. So, you can make out supernova in very distant galaxies, and this is something that can be used as a standard candle. If you can somehow find that their luminosity is the same or find some correlation between various supernova properties, you can use them as standard candles. So, this is the whole idea. Now, before going in to discussing how supernova can be used as standard candles, I will first discuss briefly certain definitions and certain quantities which are mainly relevant for optical observations. They are also relevant in other observations, but mainly relevant for optical observations. Okay. So, in the last class I had introduced the specific intensity or surface brightness. If this is a source, then the surface brightness is I nu, is denoted by I nu, is the amount of radiation coming per unit solid angle. So, it is the amount of radiation coming per unit solid angle in the frequency interval d nu, in the time interval dt, and I put a detector of size dA. It is the amount of radiation coming there. Okay. Now, for observing objects like the supernova or stars, which are essentially point objects, you cannot associate a dimension with them, what you measure is not the specific intensity, but the flux density. Okay, the quantity that you measure is the flux density. It is also given the name spectral energy density. So, each point over here, think of a source like this on the sky, the specific intensity varies from point to point on this source, right. Now, for a star or a supernova, I cannot make out the source is not resolved. My telescope beam is actually bigger than this. So, as a consequence, what I measure is the total integrated specific intensity integrated over the entire solid angle, right. So, I have to integrate the solid angle d omega over this whole source, and this is the flux f nu, or sometimes it is denoted by s nu, sometimes as f nu. Okay, this is the flux density because it is per unit frequency, or the spectral energy density. So, it is the energy watts per meter square per hertz. Okay, I have integrated over the solid angle. So, this is the quantity that is measured in principle, and quite often we use the units of 1 Jansky, particularly in radio astronomy. We use the unit of 1 Jansky. This is 10 to the power minus 26 watts per meter square per hertz. This is because the sources that we are dealing with are very weak, extremely weak sources. So, it is the unit of watts per meter square per hertz is not appropriate. Better suited is a Jansky, 10 to the power minus 26 watts per meter square per hertz. Okay, Jansky was was one of the pioneering radio astronomers, one of the people who pioneered the field of radio astronomy. Okay. So, this is the units used for this flux. So, this tells us the amount of energy in a interval of frequency delta nu coming per unit time per unit area. Area refers to that of my detector. I could equivalently, given over here the energy. Equivalently, I could also work in terms of the wavelength. Okay, so one could also define this spectral energy density using the wavelength. So I would then have f lambda and s lambda. These are defined so that the energy dE is s lambda into dA dt into d lambda. You could then use the relation between d nu and d lambda and work out the relation between s nu and s lambda. So s lambda is c by lambda square s nu. Okay, so if I work in terms of wavelength, I get a certain thing. If I work in terms of frequencies, I get something else. So this is just to get the notation clear, because if you look at the literature, you will find all kinds of things being used. So this is the flux density or the spectral energy density, which in principle is what you could measure from the earth. What is actually measured? Observation, what the quantity in which terms of which the optical observations are discussed is the apparent magnitude. This is something whose definition goes back to the ancient Greek astronomers. The ancient Greek astronomers observed the night sky with their eyes visually, and they classified the stars according to their brightness. The brightest stars, they said, were magnitude 1, and then the fainter ones were magnitude 2, and then even fainter ones were magnitude 3. They divided them into equal, as far as they could make out with their eye, they divided them into equal distances. So the brightest one was apparent magnitude 1. The faintest star that they could visually identify with the naked eye was magnitude 6, and the stars in between were divided into equal. So if what they thought was equally into magnitude, into the entire magnitude range 1 to 6. Okay, so this was done when only the eye was available for optical observations. Later on, people could use photometers, and people found that this was a logarithmic scale. The response of the eye is logarithmic. It is not a linear response. The response of eye, ear, our ear, all such devices are actually logarithmic, in the sense that if the input goes up by a power, doesn't become double, it goes up by a power, n to the power some goes up by a power, then there is a unit increase in our perception. This is required to have a large dynamical range. Our eye has an enormous dynamical range. We can see extremely faint objects, we can also see extremely bright objects. With linear devices, it is very difficult to have such a large dynamical range. So you can have a device that works very well with faint objects, but if you put a very bright source, it will get saturated. It will not be able to distinguish. Similarly, if I have something that works for very bright sources, then it will not be able to make out very faint sources. It will not record anything. Same the response of the ear and a microphone. Okay, ear has a logarithmic response. Microphone or such devices usually would like them to have a linear response. Okay, so the eye, it turned out, had a logarithmic response, and people converted this, people retained this magnitude scale. So the magnitude, it was defined to be minus 2.5. So the whole thing had been defined in such a way so that it turned out that magnitude was minus 2.5 log base 10 of the flux from the source divided by some value f0. Okay, the value f0 sets the 0 point of the magnitude scale. So when the flux is f0, you get a source of 0 magnitude. Okay, or equivalently, it is minus 2.5 log f plus a constant. Okay, so there are two things which we have to note about this. The first thing is that the fainter the object, the larger the magnitude. right? That is the whole magnitude scale. And in optical astronomy, if you are dealing with optical data, all the data, what the measurements are always quoted in terms of magnitudes. Okay, so it's very important that we really understand what this is, otherwise we will not be able to make out any optical data. So the larger the magnitude, the fainter the source, the smaller the flux. Okay. The 0 point, how is the 0 point set? So the 0 point information is there in this constant C, and at the end of this, towards the end, I shall tell you how the value of C is decided. Okay. Consider two sources whose magnitudes differ by 5. So M1 is 5 plus M2, M2 plus 5. Okay, so the difference between M1 and M2 is 5. So M1 is fainter, M2 is brighter, because fainter it is, the larger the value of M. Okay, so M1 has flux F1, M2 has flux F2. So the flux of M1 and of these two sources 1 and 2 are related like this, right? M1 is minus 2.5 log F1, so I have just put it in the denominator, so the minus sign does not appear. So what we have is 5 is equal to this, or log of F2 by F1 is 2, which tells us that F2 is 100 times F1. Okay, so there is a source of a certain magnitude, there is another source whose magnitude is 5 more. That means its flux is 100 times less. An increase of 5 in the magnitude means the flux has gone down by a factor of 100. Okay, this is a point which is worth keeping in mind. Whenever you see some data, if you have a magnitude scale, you can easily convert it to flux. So magnitude goes up by 5, the flux has gone down 100 times. Okay. Now another definition, the absolute magnitude. Now the magnitude apparent magnitude refers to the flux received from the source. Okay. Now we know that the flux is related to the luminosity as L by 4 pi d square. So I have a source of luminosity L at a distance d, the magnitude is going to be minus 2.5 log L by 4 pi d square plus the constant C. Okay. Now the same source, if I keep at a distance capital D instead of small d, then its magnitude is going to be the same thing, just the capital M replacing the small m. And subtracting these two, I can get rid of this constant. So the apparent magnitude minus this capital M is equal to 5 log the ratio of the small d to capital D. The 5 comes because of the square over here. Now by absolute magnitude, we refer to the magnitude that the source would have if it were located at a distance of 10 parsecs. So if I take a source and keep it at a distance of 10 parsecs and then calculate what the flux would be and use that to calculate the magnitude, that is what is called the absolute magnitude. The apparent magnitude for a source has two things in it. It has the intrinsic luminosity, it also has the distance. The same source, if I move further and further away, it is going to get fainter and the apparent magnitude is going to increase. Okay. Now we want to define something which is an intrinsic property, which depends only on the intrinsic property, the luminosity. So this is there in the absolute magnitude. So place the source at a distance of 10 parsecs and calculate the apparent magnitude, calculate the magnitude, that is the absolute magnitude. So, the absolute magnitude is an intrinsic property of the source, and it essentially refers to the source's luminosity. Okay, so, the absolute magnitude is equivalent to the luminosity of the source, and the absolute magnitude is denoted by capital M. Okay, so, we have the apparent magnitude, which is the flux from the source, take the log, multiply by minus 2.5, and then you can add a constant. The absolute magnitude, take the same source, put it at 10 parsec, and then calculate the log and multiply by minus 2.5, put the same constant. That is the absolute magnitude. Okay, it is just the luminosity in some logarithmic units. Okay. Now, we would like the apparent magnitude, we would like the absolute magnitude to quantify the intrinsic brightness of the source, right. So, suppose we measure the apparent magnitude of a source at some frequency nu. At some frequency nu, I measure the apparent magnitude of a source. Now, if I can measure the redshift of the object, I can then determine the distance to the object. I can use that distance to calculate what the absolute magnitude should be, right. So, that should tell me the luminosity of the object at the same frequency nu where I am doing the observation. Now, there is a complication. The complication is this: when I observe at a redshift at a frequency nu and my object is at a redshift of z, in the rest frame of the object I will be actually looking at a frequency nu into 1 plus z, and I will be receiving, this is the amount of radiation that is going to be. So, when I talk of the intrinsic properties of the object, I will actually be referring to the intrinsic properties at this frequency in the object's frame of reference, whereas I would like to talk about the object's properties at this frequency. So, I have to now correct for if the spectrum, so the object that I am dealing with, its spectrum may be such that it emits a different amount at this frequency and a different amount at this frequency. I would like to characterize its intrinsic property at this frequency. So, I have a different objects at different redshifts. I would like to ask the question which is brighter, which is fainter intrinsically, compare them at different frequencies in their rest frame. I should compare the same quantity at the same frequency in the rest frame of the object. Only then would I be comparing the same thing, right. Now, if I look, but my observations I cannot do them at different frequencies, I will be doing my observation at a single frequency, and I want to compare objects at different redshifts. So, I have to correct for the fact that when I look at a different redshift, I will be probing a different part of the spectrum. So, this is what is called the K correction, and the K correction depends on the slope of the spectrum of the object that I am dealing with. If I am dealing with a galaxy whose spectrum I believe has some slope like the one shown here, then I can calculate what the K correction should be. If my source has a flat spectrum, the flux density or the luminosity does not change with nu, then there will be no K correction. Okay. So, by K correction depends on the slope of the spectrum, So, one has to correct for this effect, and this goes into the what is called the K correction, and people have calculated what the K correction should be for different kinds of objects. Okay. So, this is a point that should be borne in mind. if you are calculating the absolute magnitude, the K correction also has to be put in. Okay. So, the distance information is there in this quantity 5 log d by 10 parsec. Okay. So, in the absence of K correction, I would call this m apparent magnitude minus the absolute magnitude. So, suppose I have a standard candle, I would know what the absolute magnitude is. If I have a standard candle, I know its absolute magnitude. Standard candle, I know the luminosities, I know what I would get if I place it at 10 parsec. I can measure the apparent magnitude, and then I would have this m minus capital M apparent minus absolute magnitude. This is called the distance modulus. Okay. If I have a K correction, then I have to correct for the K correction. So, my distance modulus is going to be apparent magnitude minus the absolute magnitude minus the K correction. Okay, that is going to be by distance modulus. So, when we refer to distance modulus, it is essentially 5 log the distance divided by 10 parsec. Okay, apparent magnitude minus the absolute magnitude plus the K correction. Fine. Okay. Now, I have told you, so what, let me just recapitulate what I have told you now, until now. The quantity which you can measure in principle is the flux density or the spectral energy density. It tells me the amount of radiation coming in a small interval d nu centered at some point. Okay. And we measure it in units of magnitude, I have told you this. And then I have defined apparent magnitude, absolute magnitude, and told you about K correction. Now, in reality, what optical astronomers usually do, they really will not always be measuring this. The optical observations are usually carried out in certain bands. So, the quantity that you measure is S nu in this entire averaged over this entire band. There are other quantities that go in. So, first there is the radiation has to pass through the Earth's atmosphere, one has to correct for this. The Earth's atmospheres, the response of the Earth's atmosphere is not same at all frequencies, it has strong frequency dependence. It allows light to pass through in the visible range, but it strong ultraviolet, infrared get absorbed at higher frequencies, X-ray, etc. it gets absorbed. There are certain regions where light is allowed to pass through, certain regions where it gets absorbed. Okay. So, these bands are chosen so that it takes into account the fact that the transmittivity of the atmosphere is not the same at all frequencies. Okay. The instrumental response is not the same at all frequencies, so that also goes in. And finally, there are also filters which are placed. So, observations are done using different filters, and finally what you have is the magnitude measured in bands defined by these filters. So, optical observations are usually done for simultaneously for multiple filters, and the information that you will get is the flux density averaged over such filters. Okay. And there are different system of, so this is what, okay, this is what is called photometry, and the magnitudes that you get thereof are called photometric magnitudes. Okay. So, photometry, what you do is you measure the flux density across such filters and you have to correct for the atmospheric effects and the instrumental effects also. So, one could have different set of filters. So, people use different sets of standard filters. One I have just given one as an example over here. So, this is the Johnson UBV filter. This has been extended further, but traditionally this is what was used, UBV bands. Okay. So, U is the ultraviolet band, B is blue and V is the visual. Okay. These are three filters. So, this U filter allows the light at an effective wavelength in units of nanometers, whose value is given over here, 360 nanometers. Okay. So, it allows the light at an effective wavelength of 360 nanometers to pass through, and the width of the filter is characterized by this delta lambda 65 nanometers. This is the full width at half maxima. So, if this is my filter, full width at half maxima is, this is the maximum throughput. So, this the maximum radiation is allowed to pass through here at this frequency. The value, the delta lambda, where it falls to half, this is full width at half maxima. So, this tells you how broad your filter is. Okay. So, these are the three filters which I have just given as an example, U, B and V bands. Okay. So, they allow light to pass through only in these three bands, and this is converted to magnitude, and the magnitudes are referred to as U, B and V, and these are the photometric magnitudes. There are other photometric systems also. So, when you look at optical data, it will always tell you the photometric system which it refers to. Okay. So, here I have just given you one example of the UBV bands. So, okay. Now, the 0 point of these bands, the 0 point of the magnitude scale is something that I still have to tell you about. The 0 point of all of these bands, and typically the 0 point for most of these photometric magnitude systems, is set using a star called Vega. So, the star Vega is used to set the 0 point of the photometric system. Okay, the star Vega is used to set the 0 point of the photometric system. So, you know the value of the magnitude for the star Vega at the U band, that is given. Okay, so, if you are using this filter, UBV filter, then you can calibrate your system by measuring the magnitude of the star Vega using your apparatus, and that will give you some value. The value is known, that the system, the magnitude scale is set by setting the value of the magnitude of Vega to a certain value, and I have shown over here the calibration of the magnitude scale in a, which is set to Vega, but here I have shown the calibration in a different way. What I have shown over here is the magnitude corresponding to 1 Jansky. So, if I had a source whose flux density is 1 Jansky across this entire band, then the corresponding magnitude, value of the corresponding magnitude is 8.03. It is given over here. Okay. Similarly, a 1 Jansky flux density source would correspond to a magnitude of 9.02 in the B band and 8.01 in the V band. Okay. So, these are photometric magnitudes. Another thing which I should tell you is color. Color is refers to the ratio of the fluxes in different bands. Okay. So, you could have U minus B color, B minus V color, or U minus V color. Okay. So, the difference in magnitudes in these bands are all colors. Okay. So, if you have this kind of photometric magnitudes, you can determine the color of the source. We also have bolometric magnitudes. I have introduced what we mean by bolometry. A bolometer in principle measures the entire radiation from a source. So, you could have bolometric magnitudes if your filter has a sufficiently broad pass band, so that the entire radiation from the source is let through, then the magnitude that you would get is called the bolometric magnitude. And this is particularly relevant if the radiation from the source is mainly dominated by a certain line. So, if the radiation from the source is dominated by a particular line, and if you let the radiation in that line through, then you have essentially measured the bolometric magnitude. Okay. So, the bolometric flux, then bolometric this okay, would has dimensions watts per meter square. That Hertz part is no longer there. Okay. So, this is how you quantify the optical observations. Okay, the results optical, infrared, ultraviolet in those near the visible range. The results you will find are given in terms of magnitudes. So, now let us come back to supernova. Supernova, what are these supernova? These supernova are evolutionary. It's a stage in the evolutionary sequence of massive stars. Stars like our sun will not end up as a supernova. It will finish its hydrogen cycle, it will expand, then it will go into a helium burning phase, etc. Okay, but very massive stars, they have a stage in their life cycle where they explode essentially, the luminosity goes up tremendously, they emit an external shell that expands, and you know that the luminosity is essentially proportional to of an object which is emitting as a black body. So, just think about it, there is an object emitting as a black body from its radius, then that is the radiation that comes out. Now, if the radius increases, then the luminosity goes up. So, a supernova, in a supernova the inner core contracts and the outer shell is ejected out, which expands, and the luminosity goes up tremendously. Okay. So, the luminosity of a star increases many folds, that is a supernova, it appears as a supernova. The supernova can be classified as type 1 and type 2. So, if you have hydrogen absorption lines in the supernova emission, these are called type 2 supernova. If you have no hydrogen absorption lines, these are called type 1 supernova, and they are denoted by SNE 1 and SNE 2. The supernova of type 1, which have no hydrogen absorption lines, can be further classified as SNE 1A and 1B. I shall not go into those details of this. Now, supernova of type 1A are particularly useful for cosmology, setting the cosmological distances, determining cosmological distances. Okay. So, what are supernova of type 1A? Supernova of type 1A, it is believed, are white dwarf stars. So, you start off with two stars which form a binary. One star more massive than the other. So, the first star, this star, first burns its hydrogen and then goes through the entire sequence and becomes a white dwarf. I had shown you the HR diagram, recollect. In the HR diagram, in the extreme left, there were the white dwarfs. Okay. A white dwarf is essentially, it's a very compact small star which is maintained by the electron degeneracy pressure. The electrons are fermions. You cannot put all of them into the same energy level. So, you have to put the subsequent electrons in the higher and higher energy levels. If the higher energy electrons, they contribute to the pressure and maintain this star in equilibrium. Okay, that is the electron degeneracy pressure. Now, there is a Chandrasekhar limit, that is an upper limit on the mass beyond which this electron degeneracy pressure cannot maintain the star in equilibrium, it will collapse. So, if a star has mass more than the Chandrasekhar limit, 1.4 solar mass, the electron degeneracy pressure is not sufficient to maintain it in equilibrium, it will collapse, form a neutron star, okay, or a black hole. Now, this is so there are two stars, one of them has become a white dwarf, the other is not a white dwarf. So, this star, which is a white dwarf, is more massive than the other star, it accretes material. This accreting material can push the mass of this star above the Chandrasekhar limit, and once it does that, it becomes a supernova. The electron degeneracy pressure is no longer sufficient to maintain it in equilibrium, it collapses and it becomes a supernova. So, this is what is believed to be a supernova of type 1A. Okay. And in the supernova of type 1A, it is found that the properties are quite uniform across the entire sample. The properties of the supernova are quite uniform across the entire sample. This is what makes them particularly well suited for determining cosmological distances, acting like standard candles. Okay, their properties are quite uniform across the entire sample. Supernova type 1b, the properties are not so uniform across the entire sample, so they are not suited for cosmological distance determination, not as well suited. Okay. Now, what do you see in these supernovas? So, when the supernova explosion occurs, when the supernova is formed, there is a characteristic rise in the luminosity to a maximum value. So, the luminosity rises to a maximum value, it starts from a low value of a typical white dwarf, and then it rises to a maximum value, after which it falls gradually over an extended period of around 30 days. Okay, so which gives you a substantial amount of time to measure this. This is called the light curve of a supernova. So, it has a rise, reaches a maximum value, the luminosity, and then it falls gradually over a period of roughly 30 days. Okay. and these properties are quite uniform around the entire supernova sample. Okay. So, it is this that is used for distance determination. So, today I am going to stop over here.